Welcome back everyone to the part 6 of daily CUDA programming series, and today the topic is pretty simple. Yesterday we looked at the concepts taught in the chapter 4 of programming massively parallel processors book, and in this one we will try to solve the exercises of this um, live and try to understand how it works, what were the concepts taught in the lecture in as well as in the book, and see if we are able to solve these exercises or not. So meanwhile, let me open my calculator in my phone. It will be required for some of these problems that I have already taken the screenshot of. So these are from the chapter 4 of programming massively parallel processors book. They own all the rights to that book. So you can buy it from Amazon if you like. But moving on. We'll start in the reverse order because the last question, or in our case, the first question is very important, which is this one. So this is pretty good question. We will do it at the end. The first question is, it is given that a student is mentioning that they are able to multiply two 1024 matrices using a matrix multiplication kernel of 32 by 32 thread blocks. Now they are using a CUDA device that allows up to 512 threads per block and up to 8 blocks per SM. So first information, there are a lot of numbers given here. Let's look at them later on. The student mentions that each thread in a thread block calculates one element of the result matrix. What will be your reaction and why? So what you need to check if it is even possible to do this multiplication or not. So total number of elements in the output matrix will be 1024 times 1024, and how much is it? Let me type it in. 1024 times 1024 is 10,48,576, 1.048 million, right? And you will observe that we are only given 8 blocks per SM, but we do not know nothing else about the GPU, like how many streaming multiprocessors does it have. So we will just assume for now that there when we are invoking a grid, there are 32 by 32 blocks in it. So total number of threads will be 32 by 32 times 512, which comes out to be 32 times 512 is 524288. And since we are already given that each thread calculates one element of the result matrix, so we have only half of the threads available. So in this case, it is not possible, and the student needs to check their solution again. But if it was written that each thread calculates two elements in the result matrix, then it would have been possible. Moving on to the second one. So we have a GPU with limits 2048 threads per SM. So let me write it down. Limits are 1, 32 blocks per SM. The second is 65.536 registers per SM. Which of the following kernel characteristics specify whether the kernel can achieve full occupancy? So for full occupancy, if you remember, number of active threads divided by maximum threads possible. Since we want 100% occupancy, we can say that we are invoking 2048 threads. So in the first case, the kernel uses 128 threads per block. So we will check the first limit. For A part, blocks will be 2048 by 128, which is how much? 2048 divided by 128 is 16 blocks. So the first limit is satisfied. And how many registers? We can calculate it like this. So 16 times 128 times 30. It comes out to be 61440, which is well below our limit 2. So in this case, we can achieve full occupancy. In the second case, we are using 32 threads per block. So the blocks would be 2048 by 32. Number of blocks will come out to be 2048 divided by 32. It is 64. 64, which is more than more than the maximum kernel limit that we can have, right? We can only have 32 kernels. So if we have only 32 kernels, then we will have 32 times 32 number of threads, which is what? 1024 total threads. And each thread will use 29 registers. So around 30K registers in total for an SM. Um, in that case, the second limit is satisfied, but the first limit will fail and we will only use 32 blocks, 1024 threads. So our occupancy will be 50%, which comes out because of 1024 by 2048. So we cannot achieve full occupancy in this case. The kernel uses 256 threads per block and 34 registers per thread. So in the case C, the blocks will be 2048 by 256. It is how much? See, I can do it easily by hand, but I don't want to stress it. 8, which is well below our limit 1. Since the number of maximum blocks we can have is 32, right now we only require 8 of them. The total number of registers required would be 8 times 256 times 34, which is, let's check. Well, it is 69632, which is more than our registers. So we cannot have that. We will not achieve full occupancy in this case as well. So only first case would be the one where we can achieve the full occupancy. The limiting factor in the second case would be the number of blocks, and in the second case are the number of registers per thread. Moving on to questions number 5, 6, and 7. So a CUDA programmer says that if they launch a kernel with only 32 threads in each block, they can leave out the sync threads instruction wherever barrier synchronization is needed. Do you think this is a good idea? So if you remember, 32 threads are in a warp, and the hardware is designed such that all of the threads in a warp follow SIMT, single instruction, multiple threads. So they are at given time. This is time, some sort of, let's say T1, and in this direction they are following the operations. At a given time, all of the threads in a warp are following the or are executing the same operation, same instruction. So ideally, you can skip sync threads completely. In one of our earlier videos, we have, I guess it was atomic add. In that, when we were doing reduction, when we were down to last 32 threads in a warp, we skipped sync threads. But just to be safe, just to be safe, because there are other limitations in the hardware which comes out because of, let's say, memory read and memory load as well, and sometimes it may not be synchronized, but in theory it is. So ideally it is up to you, but I have experimented with not using sync threads, and in some of the kernels it works fine, but I have not written so many kernels where we are using 32 threads only to check what will happen if we keep sync thread. So obviously the execution time will increase, and we won't be able to take the benefit of SIMT there, and also the benefit that we can shuffle around the values in a thread and between all of the threads in a particular warp. Moving on to the sixth question. If a CUDA device SM can take up to 1536 threads and up to 4 thread blocks, which of the following configurations would result in the most number of threads in the SM? So the limitation is we can only have 1536 threads, right? If we go for the option A, 1536 divided by 128 is 12 blocks. Not possible. At most we can have 4. So ideally, instead of 1536, we can only have 4 times 128, which comes out to be 512. So in option A, we can only have 512 threads in our SM. In option B, the total number of blocks would be 1536 divided by 256, which comes out to be 6 blocks, which is more than 4. So at most, we can have 4 blocks. So total number of threads in this case will be 4 times 256, which is 1024. And in the example C, we can have 512 threads per block, which is 1536 divided by 512, which is 3. So it is well below our number of blocks limit. So maximum number of threads we can have in this case is 1536, which is, uh, let me write it down. So that 1536. In the example D, we have 1024 threads per block. So in this case, we can have only one block, right? Because if we had two blocks, we will cross 2048, which is more than our maximum number of threads allowed. In this particular question, the maximum number of threads in SM will come from 500 threads per block configuration. So this is the correct option. I was thinking of using a different color. Yeah, let's use red from now on. Assume a device that allows up to 64 blocks per SM, 2000. So the first limitation is 64 blocks, 2048 threads per SM. Indicate which of the following assignments per SM are possible. In the case in which it is possible, indicate the occupancy level. So we have 8 blocks. So the first limit is fine in all of these cases. We are well below our 64 blocks limit. So total number of threads in our first case would be, let's do it right like this. 8 times 128, 16 times 64, 32 times 32. In this case, it will be 64 times 32. In the last case, it will be 32 times 64. I'll calculate it and write it down. So 128 times 8 is 1024. 16 times 64 is, I guess, also 1024. 32, it is also 1024. Again, it is 2048. It is 32 times 64. 2048. So indicate the following assignment are possible. In this case, which is possible, indicate the occupancy level. So if we are following the first case, we are only using 8 blocks of 128 each. So the occupancy level would be 50% in these cases. And in these two cases, it will be 100%, right? I hope I am correct with this. Moving on to the next, consider a hypothetical barrier. Consider a hypothetical barrier with 8 threads executing a section of code before reaching a barrier. So there are 8 threads and so on. This is the barrier. The threads require the following amount of time to execute. They spend the rest of the time waiting for the barrier. What percentage of the thread's total execution time? So first we need to calculate. Suppose there are 8 threads, right? So total execution time will be time taken for each thread, I going from 1 to 8, right? So this is the total execution time. Or no, it is not. This is wrong. Since we are having a barrier synchronization, we need to check which is the maximum time taken thread. So 3 microseconds is the maximum time taken. Now, how much time of the thread's total execution time is spent waiting for the barrier? So total execution time will be, since all of those threads will wait till reaching 3 microseconds. So the total execution time would be 3 times 8. and what percentage of a thread's total execution time. So let's say Ti, we can sum 3 minus Ti, I going from 1 to 8 divided by 3 times 8 times 100. This should be the answer. So 3 times 8 is our total execution time for just for percentage, and this is the time taken to wait by each thread, and we are just taking a sum over all the threads, all the 8 threads. Moving on to the second question. For a vector addition, assume that the vector length is 2000. Each of the thread calculates one output element and the thread block size is 512 threads. How many threads will be in the grid? So how do you calculate the number of blocks required? In this case is n plus 512 minus 1 divided by 512, which is 2511 divided by 512, which is how much? I guess it will be around 4. 2511 divided by 512. It's 4.9. So I guess 5 threads will be 5 or 4. Sorry, 4.9. It is 5 threads will be 4 threads. What am I saying? 4 blocks will be required, and total number of threads will be 2048 threads. So total 2048 threads will be in the grid. For the previous question, how many warps do you expect to have divergence due to the boundary check on the vector length? So in a simple vector addition, we have this condition: if index, which is the global index of a thread, is less than n, then only do the addition. So since we only have 2000 elements, let's see how do we write this. So 2015 to 2047, the threads which have the ID this will be inactive, right? And 0 to 199 threads will be doing some work, and after that it will not work. So all of the warps which have a round number before 1999 will be active. They don't show, they will not show any divergence. So what is the number before 19999 that is divisible by 32? Let's start with, let's not do it like this. It will be difficult to understand. So instead of 2015, we will do it. So index the threads by 1. So 2016 to 2048 will be inactive threads. 1 to 2000 will be active threads. And let's see which is the nearest number to 2000 that is divisible by 32. So 62 times 32. It is 1984. So warps, 1984 divided by 32 is 62. The first 62 warps will be showing no divergence. And after this, when we are in the range of 1985 to wherever the next warp ends, it will show divergence. And the last warp, which is 2016 to 2048, it will not show any divergence because all of them will be inactive threads. So what is 1985 plus 32? It is 2015. I mean, we are not adding it to 1985, add it to 1984 and subtract 1 to calculate the final index. So 1985 to 2017 will show divergence because first 1718 elements will be following the if condition, and some of them will be in the else block. So I hope you understand. Then the last question is the most important one. Not too difficult, but we will try to solve it. The first is we are given this kernel and we need to solve this question. What is the number of wops in the block? Per block, sorry. So per block we have 128 threads. So number would be 128 divided by 32, which is 4. So we have 4 wops per block. What are the number of wops in the grid? So let's find out the total number of blocks that are required. So 1024 plus 128 minus 1 divided by 1024 is, did I do it right? 1024 plus 128 minus 1 divided by 128, around one block or two blocks. Oh, I divided by 1024. I was confused for a second. What did I do? 1151 divided by 128 is 8.9. So 128 times 8 is 1024. So we will have 8 blocks. What the hell am I doing? I could have directly divided 1024 by 128, not even requiring the calculator in this case. So total number of blocks will be 8. Each block has 4 wops. Total number of wops is 32. We are done with these two. For the statement on line 4, how many wops in the grid are active? And how many wops in the grid are divergent? So line 4 tells that if thread index less than 40 and greater than equal to 104, only then it will run. So in one block, thread index will go from 0 to 1 to 7. So when we are 0 to 32, 31, let's do it like this. Warp 0 in a, we are calculating at a block level, will be 0 to 31. It will be active. Warp 1, because it satisfies the condition of less than 40, will be 32 to 63. It will be active, but it will show divergence. Warp 2 will be around 64 to what, 32 is 95. I hope that is correct. So this whole block will be inactive for line 4 because it is outside the condition. And then we will have 96 to 127. Sorry. Warp 3 will be 96 to 127. It will show divergence. It will, some of the threads will be active or inactive, but it will show divergence. So per block, for line 4, 3 warps are active. There are total number of blocks are 8. So there are 24 warps that should be active in this case. I hope this calculation is correct. How many warps are divergent? How many warps in the grid are active for line 4? Let me look at this question again. In this case, yeah, I guess 3 times 8, 24 should be the answer for, sorry, 24, 3 times 8, 24 should be the answer for the first one. How many blocks in the grid are divergent? Warp 1 and warp 3 are divergent, which is 2 times 8 is 16. What is the SIMD efficiency of warp 0 of block 0? So for warp 0 of block 0, all of the elements are not divergent. They can be executed parallelly. So it is 100%. What is the SIMD efficiency of warp 1 of block 0? Warp 1 is this. So only elements from 32 to 40, which are how many? 32 to 39, sorry, will be executed, and rest of them threads will be inactive. So these are total 8. So total number of threads is 32. 8 times 100 is 25%. 25% of the threads will be active. Of warp 3, only greater than 104. So it comes out to be 24 by 32 times 100 for the case 4, it is 75% SIMD efficiency. So we have solved all all three of them. For statement on line 7, how many verbs in the grid are active? Statement on line 7. So line 7 says it will only get executed if the thread index is a even number and each other thread index has an even number. So for example, in a verb, we are from 0 to 31 or 32 to 63. Half of the threads in the verb will be active. So the entire grid will be active. So all 32 verbs will be active. How many verbs in the grid are divergent? All of them will be divergent. What is the SIMD efficiency of verb 0 of block 0? It will be 50% because only half of the elements will be executed. So this part is also done. How many iterations have no divergence in line 9? So in line 9, we have int j equals to 0, j less than 5 minus I percent 3. So j is equals to 0, j less than, or is it equals to j less than 5 minus I percent 3. Now the thread index can go from 0 to 1023. I guess there are total 1024 threads. Yeah. So the global index can go from this, and since we are dividing by 3, so I percent 3 can have 0, 1 and 2 as values. So each thread based on the index can have the remainder as 0, 1 and 2. So let's do it iteration by iteration. The first question is how many iterations have no divergence and how many have divergence? So basically the same questions. So when we are starting from j is equals to 0, uh, what can be the value of 5 minus I percent 3? Let's calculate. When I percent 3 is 0, the value can be 5. When I percent 0, I percent 3 is 1, the value can be 4. When it is 2, the value can be 3. So the first iterations when j goes from 0, 1 and 2, all of the threads will show no divergence because in that case j is always less than 3. When we reach j is equals to 4, so the condition, sorry, when we reach j is equals to 3, which of the threads can run? Can the threads with I percent 3 0 run? Let's check it out. When j is equals to 3, I percent 3 value is this. I percent value 3 is, let's say, 0. 5 minus I percent 3 value is this. So it will be 5. It will run. Those threads will run. If I percent 3 is 1, 5 minus 1 is 4. Again, this will run. If it is 2, it will be invalidating the condition which was j minus 5% I minus 5 minus I percent 3. So when we are iteration 4, where j is equals to 3, some of the threads will not run. When j is equals to 4, let's write the table again. J is equals to 4, I percent 3 value, 5 minus I percent 3 value. It can be 0, 1, 2. When it is 0, it is 4. Sorry, 5, 1, 4, 3 again. So only those threads will be running or executing where I percent 3 is 0. And the threads where I percent 3 is 1 and 2 will not run. So the first three iterations will show no divergence because all the threads can run them. The next two iterations will show divergence because only some of the threads have enough condition because of I percent 3 and j being less than 5 minus I percent 3 to get them executing. So in this case, you can see So this is a particularly good question because you understand how an if-else block can cause divergence as well as how a for loop can cause divergence just on the basis of the iterations.